Previously, we've learned about how to transfer the points from the rectangular coordinates to the polar coordinates, right? If we're given a point with the coordinates A and B and the rectangular coordinates, it means that we need to give some units to the right and some units to the up or down, right? And we're going to define the points with the A and B, which means that I need to go A units in the x direction and B units in the y direction. And the points on the polar coordinates are again given with the t coordinates, but the coordinates are going to mean different things. The first coordinate r is going to mean the distance between the point and the origin, and the theta is going to mean the angle between this line, which connects the point and the origin, and the pole, and the x-axis. X-axis is going to call the pole in the polar coordinates. If we're given the point and the polar coordinates, we can find the x and y coordinates of the same point by using the formula x is equal to the r of cosine of theta, and y is equal to the r of sine of theta. And if you're given x and y coordinates of the same point in the rectangular coordinates, we can obtain the polar coordinates of the same point using these two formulas, right? So yesterday we said, we are going to define the curves in the polar system. So do you remember how we define the curves in the rectangular system? So we usually say that, hey, curve, the equation of the curve is equal to the f of x, y is equal to the f of x. In order to draw this step by step, for example, by hand, what we need to do is, in between the region for x, between a and b, I need to divide this into many small pieces, right? And for each piece of the x, this equation, this dependency, is going to tell me what is the height of my function at this point, right? For example, I'm going through the points from a to the b. I splitted this into many small intervals, or many points between a and b. And once I'm going through the points, this equation tells me what is the height of my curve at a single point. Okay? So it's going to tell me what is the height of my curve for all the points. So if I just find the heights of the points on the x, and by connecting them, I can draw the curve given by the equation y is equal to the f of x. Okay? This is how we define the curves in the rectangular coordinates. So now we're going to define the curves differently in the polar coordinates. Is r is equal to f of theta. Okay? So the concept of drawing this is again the same. Okay? If we're given the pole, so if I would like to draw the curve, do you remember before? The argument was x, right? So x is going to change between a and b, and I splitted the interval between a and b to the many small pieces, right? Now, what is the argument? In this case, in the second case, the argument inside the function is theta, right? So the theta is going to change between theta 1 and theta 2, basically between the t angles. And I'm going to split this points between the theta 1 and theta 2, let's say theta 1 and theta 2, to the many small pieces. And for each piece of the theta, I'm going to find the points by measuring the distance from the origin. Okay? For example, for this theta, for the first theta, the point has this distance. At this theta, point has this distance. At this point has this distance, this distance, this distance, and so on. Okay? By connecting them, I'm going to get the curve, define it in the polar coordinates, with the equation r is equal to the f of theta. Do you understand this? So for each value of the theta between the theta 1 and theta 2, this dependency is going to tell me, okay, so where this point is, how much this point is far away from the origin. Okay? Previously, it used to tell me what is the height of the points for each of the axes, where I choose the points here. Now, where I choose the angles, it's going to tell me how far the points are from the origin. Okay? In this case, we're going to draw the curves like this. So we define a couple of examples of the polar curves. So one of the examples was the Cardioid. Do you remember this? What was the equation of the Cardioid? Cardioid? So r is equal to the 1 plus sine of theta. It's going to define us this curve. right? This kind of curve, roughly. So it's going to be called as a cardioid. It looks like a heart, so that is why it is called the cardioid. So we can define a different cardioid. So let's draw another one. So R is equal to 1 plus cosine of theta. It's going to be the cardioid, which is like light on the x line. It's going to be like this. Okay? So by, again, putting different values of the theta from 0 until the t pi, so we can find the points. Okay? So we can find all the points by connecting all the points defined by this curve. We can find the graph of this curve. Okay? Y is equal to the 1 plus cosine of theta. It's going to give us this kind of curve. We also define the least of the rows, right? Do you remember this? For example, if we wrote the curve as R is equal to the cosine of 2 theta, it's going to be this kind of curve. Basically, I need to put one leaf here. So the graph of this curve in the polar coordinates is going to be like this. R is equal to the cosine of 2 theta. It's the rows with 4 leaves. If you write the sine of 2 theta, it's going to be, again, the rows with 4 leaves, but it will be rotated to the pi over 4. Okay? So let's draw this. This is the graph of the curve R is equal to the sine of 2 theta. Okay? So again, so these are the examples of the polar curves, basically the curves defined in the polar coordinates, in the form R is equal to the f of theta. Okay? So today we're going to discuss how to find the areas in the polar curves, right? For example, I'm interested to know what is the area of one leaf of the rows. Or we're going to discuss what is the arc length of the curves, right? What is the length of this curves? Okay? So basically the calculus, how to find the tangent lines and so on. Okay? So basically, do you see that this can, like the curve, the polar coordinates, can be explained as a parametric equations? And we've learned about a lot of formulas, like a lot of techniques for the parametric equations, right? How to find the areas, how to find the tangent lines, the arc lengths, surface areas, and so on. We're going to adopt those formulas for the polar curves. Okay? So let's start with the derivative of the polar curves. Basically, the tangent lines to the polar curves, right? Do you remember the 4 steps in order to find the tangent lines? Tangent lines. The step number 1 is to write down the equation of the tangent line as mx plus b, right? Step number 2 was to find the m, which is the slope. Do you remember how to find the slope? So we need to find the derivative of the y with respect to the x and evaluate this at the given theta, right? Theta in our case is the parameter, okay? So step number 3 is we need to find the coordinates of the point in the rectangular coordinate system, right? x0 and y0. So x0 can be found as, how I can find the x0? By multiplying r of theta cosine of theta, and y0 can be written as r of theta and sine of theta. Okay? And step number 4 is we need to find the y-intercept. So if we substitute those points, x0 and y0, to the equation of the tangent line, to this equation should be satisfied. Right? If you substitute y0 to the left, the right-hand side part should be equal to the m x0 plus the b. If m is known, x0 and y0 are known, we can find a b by subtracting mx0 from the y0. Okay? The only problem is how to find the derivative of the y. Okay? So in order to find the derivative of the y with respect to the x, so let's let's adopt the parametric derivatives to the polar curves. Okay? So do you remember what was the parametric equation for the polar curves? It's like if your curve in the parametric system, in the polar coordinates, is given as r is equal to the f of theta, then you can write down the curve parametrically as x is equal to the f of theta, cosine of theta, and y can be written as r of theta, sine of theta. For example, if the curve is given as 1 plus sine of theta, do you remember that this looks like a cardioid, right? So let's say I would like to define this curve parametrically using x and y. Do you remember what was the parametric equation? Where we would like to describe the curves using the set value, using the parameter. Okay? So if I would like to describe this curve using the x and y two functions, it's going to be x is equal to the 1 plus sine of theta multiplied to the cosine of theta, because I'm just going to plug this r to here. Okay? And y is going to be as 1 plus sine of theta multiplied to the sine of theta. I'm going to plug this r to here. And I'm going to get the parametric equation of the cardioid. Okay? Which depends on x and y, which depends on the theta. So depending on the values of the theta, I'm going to find the coordinates of the points. Do you remember what we did in order to draw the curves in the polar coordinates? So we defined a lot of thetas. For all of the values of the thetas, for example, between 0 and t pi, we found the value of the r. Right? So for example, theta in this case is going to change from 0 to the t pi. I'm going to find a lot of points between 0 and t pi. And for each value of the theta, I'm going to calculate the r. It's going to be the distance of the points. If I connect them, I can draw the cardioid. Okay? So I can draw the same cardioid using the parametric equations. Where I write the x like this and y like this, what I'm going to do is I'm going to define a lot of thetas again between 0 and t pi. And for each value of the theta, I'm going to calculate the x and y coordinates of the points. Okay? By finding x and y coordinates of the points, and by connecting them, I can do the cardioid again. Okay? So do you remember what was the derivative of the parametric curve? So what is the y prime? So this was like a y dot divided to the x dot, right? Or basically, derivative of the y with respect to the x can be written as derivative of the y with respect to the parameter. In our case, it's a theta, right? So previously it was t, now it is theta, right? Divided to the derivative of the x with respect to the theta, okay? So now let's find what is the derivative of the y in this case, or in general. In general case, what is the derivative of the y? So if the y is equal to the r multiplied to the sine of theta, what is the derivative of the y? So we need to use the multiplication rule, right? Because r can be any function of the theta. For example, it might be 1 plus sine of theta. So in general case, we don't know this. Okay, this is given some function of the theta. For example, this might be like this. Okay, so here I've got the y is equal to the multiplication of the two functions, which depends on the theta. Okay, so that is why derivative of the y with respect to the theta. So let me write this derivative of the y with respect to the theta. It's going to be the r prime, right, or derivative of the r with respect to the theta, multiplied to the sine of theta, plus r multiplied to the derivative of the sine, which is cosine. Right? Yes? For our example, so what is this? Derivative of the y with respect to the theta. It's going to be derivative of the r. So if the r is given like this, what is the derivative of the r with respect to the theta? What is the derivative of the r with respect to the cosine of theta? Right? So this is 1. So derivative of the 1 is 0. Derivative of the sine is cosine of theta. So I just need to plug the cosine of theta to here. Right? So cosine of theta multiplied to the sine of theta plus 1 plus sine of theta multiplied to the cosine of theta. Okay? So what is the derivative of the x? This x with respect to the theta. So if the x is given as r multiplied to the cosine of theta in general case, what is the derivative of the x with respect to the theta? So again, you need to know that r here is some function of the theta, right? It is not a constant. For example, this might be 1 plus sine of theta. Okay? So what is the derivative of the x with respect to the theta? It's going to be a derivative of the first function, which is dr d theta, multiplied to the cosine of theta, plus the first function multiplied to the derivative of the second. What is the derivative of the second function? Minus sine of theta. Right? For our example, where x is equal to the 1 plus sine of theta multiplied to the cosine of theta, I need to apply here dr d theta as cosine of theta. Okay? Derivative of the x with respect to the theta, it's going to be cosine of theta multiplied to the cosine of theta minus 1 plus sine of theta multiplied to the sine of theta. Okay? This is how we are going to find the derivatives of the y and x with respect to the theta. Okay? Once you find them, you need to divide the derivative of the y with respect to the theta to the derivative of the x with respect to the theta in order to find the derivative of the y with respect to the x. Okay? So let's do an example. So we're given a cardioid. We would like to find the equation of the tangent line at theta is equal to the pi over 3. Okay? Find the equation of the tangent line. So again, we need to do 4 steps, right? Step number 1 is we need to write down the equation in the form mx plus b. In step number 2, we need to write down the f prime, and we need to evaluate this at the theta is equal to the pi over 3, right? So we say that the f prime, y prime, is equal to dy d theta divided to the dx d theta. So what is the dy d theta? It is this value, right? Cosine, so equation of the tangent line to the curve. Cosine of theta multiplied to the sine of theta plus 1 plus sine of theta multiplied to the cosine of theta. Divided to cosine of theta multiplied to the cosine of theta minus 1 plus sine of theta multiplied to the sine of theta. So is this going to be the slope of the line? No, actually, this is the function of the theta, right? So in order to know what is the slope of the line, I need to evaluate this at the theta is equal to the pi over 3, right? So actually, this is going to tell you the slope of the tangent lines depending on the theta. Okay? If you would draw the cardioid, again, for different values of the theta, it would tell you the slope of the lines, the tangent lines, right? For example, if you would draw the tangent line at here, so what is the value of the theta where I'm going to draw the tangent line like this? What is the theta here? It's going to be pi over 2, right? So the slope of the tangent line is equal to the 0, right? So let's check this. If I would substitute the pi over 2 to this equation, right? So what is the cosine of theta at the pi over 2? Is 0, right? And the cosine of theta at the pi over 2, this one is 0, right? 0 plus 0 divided to any number. So this is going to be not 0 in the denominator. You're going to have 0, okay? So this y prime is going to tell us the slope of the tangent lines at the point theta, okay? If I would like to draw a tangent line at the pi over 3, right? It's going to be here, right? So pi over 3 is Somewhere here. Okay. I would like to find the tangent line here. Okay, roughly like this. So let us calculate its slope. So maybe my graph is not perfect. So let's calculate mathematically what is the slope of this tangent line. In order to do this, we need to calculate this formula for the theta is equal to pi over 3. Okay? So what is the cosine of pi over 3? So 1 over t multiplied to the square root of 3, 1 over t, over t, plus t plus square root of 3 over t, right? Because 1 plus square root of 3 over t, it can be written as a t plus square root of 3 over t, multiplied to the 1 over t, divided t. 1 over t multiplied to the 1 over t, minus t plus square root of 3 over t, multiplied to the square root of 3 over t. Okay, let's do a little bit simplifications. We can divide or we can multiply all the terms here to the 4, right? So it's going to be square root of 3 plus t plus square root of 3, right? Divided to 1 minus t square root of 3 minus 3, right? So it's going to be written as t square root of 3 plus t. On the denominator, we're going to have, what is the 1 minus 3? Minus t square root of 3. What do you think? Are the numerator looks like a denominator? A little bit, okay. So they are exactly the same unless I'm just multiplying the denominator to the minus 1, right? So it's going to be minus 1, right? Because I can write this as a t square root of 3 plus t divided to the t plus t square root of 3, right? The slope of this tangent line is equal to the minus 1, right? It looks like a minus 1 slope, right? Okay, what is the next step? Step number 3 is we need to find this point, the coordinates of this point, x coordinate and y coordinate, right? Because I'm having the one more unknown, which is b. So if I can find the coordinates of this point, and I also know if I know the equation of the tangent line, if I substitute this point to the equation, this equation should be satisfied because this curve is passing through this point. Okay, so x0 can be found as r of theta multiplied as the cosine of theta, right? Do you remember what was the r of theta? It was 1 plus sine of theta multiplied as the cosine of theta. We need to evaluate this at the theta is equal to the pi over 3, right? So this is going to be t plus square root of 3 over t, right? Multiplied to the 1 over t, or simply t plus square root of 3 over 4. Okay, x coordinate of the point, this point, where the theta is equal to the pi over 3 is equal to this one. So y is equal to r of theta multiplied to the sine of theta. It's going to be 1 plus sine of theta multiplied to the sine of theta. And we need to evaluate this at the point theta is equal to the pi over 3. If you put this, you're going to have t plus square root of 3 over t multiplied to the square root of 3 over t, or you can write this as 3 plus t square root of 3 over 4, right? We found the x coordinate and y coordinate of this point, where the theta, the angle between the pole and this line, is going to be pi over 3. Okay, this angle is pi over 3. So now we need to find the b, right, y-intercept. So at which point of the y, this line is going to cross with the y-axis, okay? Where this line is crossing with the y-axis. So step number 4. So x0 and y0 are in the line, are lying in this line, mx plus b. So that is why they should satisfy this equation. So y0 minus mx0 is going to be equal to the b. I need to substitute here the y0, which is equal to the 3 plus t square root of 3 over 4. And do you remember what was the m? Minus 1. We calculated this in the step number 2. And x0 is going to be t plus square root of 3 over 4, right? So if I give the common, they have the common denominator, I can just sum them. This is going to be 3 plus t square root of 3. This minus with this minus is going to be plus, right? And it's going to be t plus square root of 3 divided to the 4, or simply 5 plus 3 square root of 3 over 4, right? This is going to be the y-intercept. So the equation of the tangent line to the cardioid at the point pi over 3 can be written as y is equal to minus x, right? mx plus b, plus 5 plus 3 square root of 3 over 4. So this is the equation of the tangent line to the cardioid at pi over 3.